Have you ever wondered how to take a rigid piece of metal and bend it exactly how you want it in Houdini? Well, stick around and I'll show you how to do it step by step, node by node. And if it's just your first time tuning into this channel, my name is Matt Sola, and on this channel I learned and I teach destruction effects in Houdini and Unreal Engine 5. And your help, either by liking, subscribing, or commenting a nice thing or a question, helps a long way. And it helps me help you. Alright, let's jump right in. And I think the first pit stop that we should take is understand the logic and the workflow behind this effect, so that we can kind of re-engineer and reconstruct the ideology, how it was made. So when we go into the nuts and bolts and bring down all the nodes and properties and things like that, we understand from the high level how it was made and how all those pieces come together. So the step number one, as you can tell by this node, is base mesh preparation. And that's our first thing, is to model the underlying geometry that is going to be simulated. And along with the geometry, or the metal sheet in this case, also we need to model these things right here, which are these, you can think of them as beams, okay? Metal beams. And that is going to help us, and that is going to kind of work as a collision geometry, if you will. And when the metal sheet sort of collides with it, you see this bending effect on the screen. Okay, so that helps make the bend. All right, when we create the base mesh itself, the second step is fracturing this metal sheet. We need to give it sort of like a fracture pattern, or a breakup pattern that's going to help us create this effect. We're going to talk about that later. And once we have the fracture done, the next thing we need to create is these constraints. Okay, and if I press play, you'll see it kind of looks pretty fun. Okay, so that is what constraints. And if you've never heard of constraints yet, what constraints are is very simple. They are relationship between fractured pieces. So if I put my display flag on the pieces, these are the fractured pieces, and the constraints are basically a relationship between those pieces, and they help establish the connection, how they should move and react when simmed. All right, once you have those done, the last step is transferring the high resolution geometry onto the low resolution geometry. So the effect looks pretty cool, and that we can use it in game engines like Unreal Engine 5 or another real-time platforms, basically. All right, I think we have the high-level thinking understood. I think what we can do is jump in and start recreating this effect. And I invite you to go along with me. And as I always like to say, it all begins with the geometry container, which is surface operator level. So we have to drop that down onto our network view and dive right in. Since I have it already created, I'm going to dive in one of mine. And when I do, obviously I can see all of the nodes dropped that basically make up this effect, right? So what I will do is I will mouse over to the clean side. And the first thing, as we established, we need a geometry for the sheet. So I'm going to pull out a box node by tapping tab on my keyboard. That let me choose this node. And what this node usually does is it creates a sort of a box on the screen, and that we can adjust properties to our liking to create this sort of metal sheet look. So I'm going to start with X direction. That's going to give me this depth to the metal sheet. And usually the metal sheets are very thin, right? So we want to replicate that look. Next thing I want to do is maybe play around with Y a bit. Something like this, 1.5. And let's see what the Z does. Okay, so that's that. I'm going to probably do something 1.2. All right, now I'm quite happy with the way my metal sheet looks. And always I can come back and readjust those sliders the way my heart wants. The next step in the process is, actually I'm going to comment it out by tapping Control middle mouse on the node, and that's going to allow me to comment out this node so we could always read our network better. And this is actually my preferred way of learning Houdini. And I'm going to say I'm creating a metal sheet. And when I do that and click Show Comments in Network box, you see I have commented out my node, and I'm going to refer to this later. Okay, what is the next step? Well, the next step is I propose we add a few more points than we already have. So we have 0.1, 0.2, 0.3, all the way upwards to the 0.7 available on this metal sheet. Well, I want more than that. Well, I want to shatter my geometry with the Voronoi fracture so we can have this breakage pattern, right? So I want something like this and this and this. So I want my geometry being broke up in those sort of patterns. Well, to do that, the first thing I need to do is bring out a scatter node. Again, I'm hitting tab on my keyboard and from the node menu choosing scatter. And scatter node comes in handy if I untick the points here. And scatter node comes in handy when you want to do exactly that. Scatter a bunch of points onto the mesh. And you can kind of tell Houdini how many points you want by this force total count. The lower you go, the lower the points are. I'm gonna kind of keep it to the default by clicking Control middle wheel onto it, and that's going to default it back to the original values. So I'm happy with that. And the next one, or the next step, is actually dropping down a Voronoi Fracture node, which comes in handy when you want to basically break up the geometry based on these input points. So if we take a closer look at the Voronoi Fracture node, we can see it has two inputs. One is for the Voronoi cells, which requires points, and the other one is geometry itself. So I'm going to plug the first input that comes from scatter node, and the second points is actually I'm going to use the scatter onto the points. And what else I need? Yes, I need the box connected to the Voronoi fracture, and when I do that, I can see the fracture forming on my geometry. As you just noticed, it's very hard to read what you've done without commenting out everything. So I'm going to click Control middle mouse on the scatter node, and I'm going to say I'm scattering points on my metal sheet. And I recommend you do the same if you ever want to come back to your networks and read what you've done and change around priorities. And I'm going to do the same for Voronoi fracture here. And the Voronoi fracture is basically I'm fracturing my metal sheet based on points. Okay. Show comments in the box, and voila, we have our metal sheet made and fractured. Well, the next step is we need constraints. Okay, the constraints again are a relationship between pieces, and usually a node called constraints, RBD constraints from rules, come in handy whenever you want to create your manual constraint network. So when I put my display flag to this node, I press P on my keyboard, what we can see immediately is that we have already created our constraint network. And we can change the connection type by going to the surface points. We can do hinges and center of mass that we just looked at. We want surface points at the moment. Why? Because surface points connect geometry sort of like in all these directions. And if I actually look at my previous network, I have commented out very cleverly. And I've said that I'm creating constraints between points and tagging them, okay? And I can actually use the same and save us a little bit of time here. So I'm gonna Control middle click, say I'm creating constraints between points and tagging them. Well, you're probably asking yourself, what tagging? Well, we haven't done really any tagging yet, so that's our next step. All right, how do we tag the points? Well, there's a group type called primitive group or tag from the dropdown. Well, if we choose tag, we have created a tag that says connectors. You can basically choose your own name. I'm going to stick with connectors, and I'm going to leave everything as is. Okay, next step in the process is we need to actually tell Houdini what these constraints are supposed to be. Are they glue, rigid? Are they going to be soft, meaning elastic and have a little bit of bend in them? Or they're going to be any other constraint type? Well, that's our next step. So I'm going to take out the first pin from the RBD constraint rules node, and I'm going to use a node called RBD constraint properties. Okay, RBD constraint properties. And when I basically drop this down node, automatic connection is going to be established, and we're going to have 3 inputs. So basically geometry, constraints, and the proxy geometry. And actually, the second node, Voronoi Fracture, also kind of wants to make a connection between the pink connectors. And usually it's not necessary because I don't think Voronoi Fracture probably does create, yes, it does create a constraint, but we don't actually need them because now we're creating our own constraints that were called surface points, basically surface point constraints. And then we're tagging our constraints by using some of the available settings here. And what we want to do is not only use glue constraints, but we want to switch constraints. We want to switch them from glue to the soft, meaning we want some elasticity in. So when the glue constraints break, we turn into the soft constraints. So I'm going to choose from switch constraints, enable. That automatically is going to populate everything as this. And that's exactly what we need. And into the strength, I want to set it to 1. Propagation rate, I want to 10. Propagation iterations to 1, stiffness to 10. Maybe we can use some of the plasticity down from this drop down, so I'm going to enable that. And actually, angular, so let's see what else we need from here. Damping ratio, and actually to help me out with that, what I can do is I can use RBD constraint properties node that I already used in my previous sim. And so we don't waste any time. Basically, it's already commented out. And let's see. Break any connections by holding Y on my keyboard. And I'm going to reconnect this. I'm going to pull up the settings for the node. And I'm going to basically guide you through what I've done here. Well, at the top constraint group, I use the constraint tag connector. Usually when you drop down your node, you're not going to see anything because well, you haven't changed the setting here. And when you choose basically this, you can say connectors, and that's going to use this group that we have created here. Okay, so that's very important. Next is glue constraint, which is basically switching to the soft constraints. We're having collisions, strength is to 1, half-life 0.1, propagation rate 1, stiffness 10, angular stiffness 10, and plasticity. You can enable it, you can disable it, you can always change it later down the line. So, okay, what is the next step after the constraint properties now? Well, I propose we drop down RBD bullet solver. I'm going to say RBD bullet solver is going to establish new connections between one node and another one. And if I put my display flag to it, recenter my view by clicking space H on my keyboard, pressing P to get the settings back, and always want to kind of reframe to the first frame. And when I do that, usually a simulation resets itself and everything looks how it should look. Okay, so probably the first thing that I want to do now is I want to somehow make this geometry fall from sky a little bit. Well, the way I can do this, I can go into the box node, press P on my keyboard, and use the center Y parameter. And when I use that, actually I can recenter my geometry in the Y direction, and I also want to give it a little bit of rotation. So randomly we can choose any number that we want, something like this. Maybe this could be 20 or minus 20, something like this. Okay, great. the next thing that we need to do is, remember, we talked about how we need a collision geometry. So I propose we create a few beams. That is done by using a box node again. Very super simple. I'm going to put display flag to my box node. I'm going to reference the RBD bullet solver so we actually see what we're doing on the screen. And this doesn't have to be super scientific. We're just eyeing out the dimensions so we can just quickly see the effect. So maybe this can be something like 0.4, as is the y direction. And this seems to be like something like that looks like a beam. But I perhaps would want two beams. Maybe actually one beam could do. But if you want two beams, all you need to do is take the box node, press Ctrl C on your keyboard, press Ctrl V to duplicate it, or alternatively, you can select the node, hold down Alt, drag it down, and that's how you can make a duplication. And if you want to get rid of the previous one, Alt X to cut it, and that's how you get rid of that. And obviously, we want to put the display flag to this node, select the newly created node, and somehow make this, bar a little bit misaligned, so it has a little bit different position in space. So we don't, okay, something like this perhaps would do. Okay, well, the question now is how do we combine them and where do we put them inside of the RBD solver so we can see the collision? Well, that usually is done with this input here. Not the guided sim, but the second from the end, which says, collision geometry. So we plug that in, press R on our keyboard, press P to get the settings back for this node, and there we go. We have a collision geometry. But I'm not very happy with this because I'm created the second box that I want to merge with this one. So the way we join them in is with the merge node. So I'm going to take this pin, plug it in, second pin, put my display flag to it, make sure I'm on the display mode here, flat shaded with wires. And now when I basically put a merge node inside of the sim, put my display flag to it, and there we go, I can see my collision geometry. And I wonder why I don't see both of them. Hang on, maybe I need to reset the sim. P on my keyboard with RBD Pulse reset simulation. There we go. Usually that is a big problem. Newcomers come in, they create all these things and connect everything to RBD bullet solver, and things don't look the way they should be. And that is usually done by either clicking on this button or reset simulation, and that should fix most of your problems. All right, so I propose we open up the RBD bullet solver, and what we need to do now is go to the constraint tab, and we want to specify under the constraint names that we're using both of the constraints that we just set for our geometry, which were glue and soft. Right now they're soft and hard, which is not quite correct, so we want to soft and glue from the drop-down menu, or you can type it in using your keyboard, doesn't really matter. Well, you can use distance threshold, but what we're going to do is we're going to use a specific rule that's going to govern how we change the constraints. At the moment, we're deleting constraints, but again, I want to switch to the next constraints when the breakage happens. And this setting is going to help me do that, along with the vex snippet that I'm going to use. So I'm going to tick this little vex snippet dialog box, and that's going to help me write what I need to write. And actually, I have a vex snippet already created for myself, and I'm gonna paste it right here. If you don't want to use a vex snippet, you're free to use either distance threshold, some are set like this, or angle threshold, set something like here, and that can give you a similar effect. But I'm gonna use a vex expression like this, and actually if I zoom in into this, you can take a screenshot or type it out if you want. Okay, so that's what I'm going to use as a rule that's going to help me create basically the bend effect. So I'm going to press P on my keyboard, and I think what we can do now is run the sim, but I don't really like that I see this constrained geometry onto it. It's kind of distracting. I wonder what if we kind of get rid of it. And we can by going into the visualization and constraint geometry, and that's gonna help us with that. Also, I don't like that the collision geometry is blue. I usually like something like this. So this looks a little bit better for me. So I think what we can do now is we can press play and see how this looks. Okay, this looks pretty good for the start. Let's play back once again. Okay, we're in a really good standing. And what next we need to do? Well, remember we talked about the step where we need to translate from the high resolution geometry onto the low res geometry, which is box here. Remember? Oops, box here. So we need to transfer from here back to here. So how is that done? Well, it is done by using a combination of 3 nodes, or 2 nodes actually. The first one is going to be a time shift node, and the second is going to be not time, but is going to be a point deform node. And the way this works is very simple. And actually, I'm not gonna give color. Okay. So the point deform is going to, the first input is going to go into our original mesh, which is going to be Voronoi Fracture. Actually, let's do this. I think I need more divisions onto my box, so I'm gonna go back to the box. I'm gonna say 40 by 40 by 40. And what is that going to do is it's going to basically give more resolution to my geometry. So when I transfer the animation from the high resolution to lower resolution, it kind of has a little bit better look. So these are the settings I'm going to use. And what I want to do is I want to use my time shift node. I'm going to select, press P on my keyboard, and I want to get rid of this frame 42. I want to go back to the first frame, and I want to Control Shift click onto this, Control Shift left mouse click, and that's going to get rid of this animation, set animation. So I'm going to say, you know what? I want to take the high resolution geometry that comes out of the RBD bullet solver, and I want to freeze it, okay? And I want to pipe that into the point deform rest point lattice, okay? So I want the high res geometry work as basically a freeze geometry. Next thing that I want to do is I want to take out deform point pin like this, and I want to connect it to my RBD bullet solver, to the same basically high-res geometry. So probably you're wondering how I created this pin. Well, the way you can create this pin is hold down Alt, click on this little thing, and there you go. You have your pin. Also, you can do something like Shift S, and by using Shift S, you can change the wire from sort of like this line pattern to make it more smooth out, basically. Well, there's one pin left that hasn't been connected to anywhere. So the question is, where does it connect to? Well, we're going to use the box node, which is this resolution here. So I'm going to say, please take this geometry and with the point deform node, transfer the animation to it. So now, if I have done my job right, everything should work. And I'm not seeing the collision geometry at the moment, and that's because I'm just outputting the point deform. Actually, I can use something like a merge node at the bottom to merge the results of the point deform node, and I'm going to use these two guys, which are the collision geometry for the RBD bullet solver. Take the output of the merge, put it inside of the merge here, and make sure I'm in the shaded mode on my screen here. And now we do this and hope it works. And already it looks like it does. Okay, we give a few seconds for Houdini to think through our animation, to pull all of the data that we have created upstream and say, please RBD bullet solver, take our upstream work and calculate for us how this metal sheet should bend. And there we go. That's how we have created a metal bending effect inside of Houdini. Now, you probably have questions like how I can adjust properties to make it look a little bit different. Maybe it needs to be a little bit more rigid and things like that. And well, if I hit P on my keyboard, go back to the RBD bullet solver, and under the collision tab, the constraint tab, we created this code. And if I click on this little menu that says create spare parameters for each unique call, I click there and go back to the constraints, and you see there is, actually I'm going to initiate my pen, hang on, there's a newly created basically slider that says break threshold, and actually I can set it to 1, or you can set it to any other value really, and that it can help you control how this effect looks like. You know, now it looks kind of rigid, a little bit more rigid. Actually it looks the same, no? Or we can do something like 0.3, see how that looks. Okay, so basically sky is the limit with these settings. I'm going to show you another settings you can actually go ahead and change. So glue usually stays at 1 because we want it to break quickly. Stiffness, usually it's at 10 for this effect. Angular stiffness, actually we can try and enable angular plasticity a little bit. Actually I wasn't sure, I'm on the first frame, so Houdini doesn't calculate everything. So I'm going to enable angular plasticity and recalculate the settings, or recalculate the sim. Okay, let's play. So these are the settings basically that I could take a whole day to go through these settings, but the things you can basically change are, you know, what you find in RBD constraint properties here. You change the angular stiffness, you change thresholds, you change angular thresholds, angular rates. Basically all these settings that you see here, there is no rule that you have to follow. It's basically just changing sliders there, changing sliders in the RBD bullet solver. Maybe you don't want to use vex snippet, maybe you want to use something like angle threshold instead. You're more than welcome to do that. You can use distance threshold and see how these properties affect your created simulation. But I think for this tutorial, I think we're good. The most important thing was to show you the workflow and basically the process that you have to follow to create this effect, and then, you know, the ball's in your court and you can make it your own and turn the sliders up, down, however you want, and just play around with it and have fun. So that was for this effect today. I want to say thank you so much for taking your time and learning this together with me. And with that said, I'm gonna see you in the next one. Thank you.